All right, everybody, we're back in part 5 now of chapter 12, non-renewable energy resources. And today we're going to be talking about nuclear energy. We'll discuss the use of fission in nuclear reactors. We'll talk also about the advantages and disadvantages of nuclear energy. Really briefly, we'll touch upon fusion power. And our objective today, we're going to be able to discuss the uses and consequences of using nuclear fuels. So first of all, before we go into detail about nuclear reactors, we have to understand the basic fission reaction. And so again, we're going to go back to general science freshman year, talking about fission. This is when a nuclear reaction is when we're going to have a neutron strikes a relatively large atomic nucleus, which then splits into two or more parts. So this picture up here shows us this yellow neutron right there, and it's going to be collided with this nucleus of a uranium-235 atom right here. And what's going to happen is that big uranium nucleus is going to split into two fission fragments. All right, one over here, one over here. It's also going to release several neutrons, here, here, and here. Okay, and those neutrons, those are going to move on, and they're going to find new nuclei to bombard. And when those neutrons bombard, those are going to release even more nuclei and even more neutrons. And so this process keeps happening and happening and happening, and this is the chain reaction that we're talking about in a fission reaction. On page 332 in your book, that goes through the actual chemical reaction with reactants and products. So make sure that you're familiar with that and you can take a look. So now talking about nuclear reactors, this is where fission happens. These are the nuclear power plants. And so we've got our fuel rods. These are the tubes that are shaped like cylinders that house the nuclear fuel that are used in the power plant. So those are the fuel rods. And what happens is nuclear power plants work by using heat from nuclear fission to heat water. That water produces steam. Steam turns the turbine, which turns the generator. So very similar to a fossil fuel power plant, except this time the heat's not being generated from combustion. Instead, the heat is coming from fission. And I mentioned before that this fission reaction is a chain reaction, and it can go out of control if the reaction is not regulated. So to make sure that the reaction doesn't go out of control, we use control rods. And those are devices that can be inserted between the fuel rods to absorb excess neutrons, and thus they'll slow or stop the fission reaction. So the control rods do exactly what they say. They're able to control the fission reaction, and the fuel rods, that's what has those are the rods that have the actual fuel. And this picture here is a basic setup of a nuclear reactor. So over here we've got our control rods, and this is again where the uranium fuel is. That's where the reaction's happening. Okay, and we can channel the heat that's generated, and we can use that heat to make steam. The steam goes under pressure here, spins the turbine over here, and turbine's connected to a generator, and that generator makes the electricity. And again, that's a basic nuclear reactor that's here in the United States. So advantages and disadvantages of nuclear power. Talking about the advantages first, no air pollution is produced. We don't make CO2. We don't make sulfur dioxide or nitrous oxide. We're not polluting the air here. That's a really important distinction. And a lot of I remember a lot of people in general science in our class had this misconception where again we're not polluting the air in nuclear power plants. We can also really limit our dependency on foreign oil. If we don't have to import as much foreign oil, if we can get our electricity and get our transportation energy from another source, then hey, that's great, and we don't have to get ourselves involved in wars that are halfway around the world. Disadvantages, though, possibility of accidents and radioactive waste. Okay, we'll talk about both of these on the next slide. So first of all, talking about accidents, there's been two very well-known accidents. First of all, 3 Mile Island, right here in the United States in Pennsylvania, and this happened in the late 1970s. What happened here was there was a lack of cooling water in the reactor core. So if there wasn't that water to cool the reactor down, the reactor heated up. That's called a meltdown. and 3 Mile Island experienced a partial meltdown. There was a certain amount of radiation that was released, and there was an evacuation of children and pregnant women. 200 other thousand people also chose to evacuate, and coincidentally, this incident corresponded to the release of a film called The China Syndrome. Check it out if you ever get the chance. It talks about safety violations and a near catastrophe at a nuclear power plant. It was all fictional, but it corresponded ironically with this incident. The other very famous incident happened in 1986, Chernobyl in the Soviet Union. Here, operators deliberately disconnected emergency cooling systems and removed the control rods. So here, this happened on purpose. In 3 Mile Island, the operators, they didn't notice that a cooling valve had closed in 3 Mile Island. But in Chernobyl, the operators deliberately disconnected the emergency cooling system. They removed the control rods. There was an explosion of fire, 31 instantly killed. And the weather patterns with the wind carried the radiation to contaminate crops, milk, all kinds of agricultural land, and all throughout the Soviet Union. Approximately 4,000 cancer deaths over the next 50 years from radiation exposure. A huge cleanup had to be undergone. There were approximately 5,000 cases of thyroid cancer, most of them among children who were under 18 at the time of the incident. So huge disasters here with risks with nuclear power. The other disadvantage of nuclear power is radioactive waste, and radioactive waste happens once the nuclear fuel can't produce enough heat to be used in the power plant, but it continues to emit radioactivity. And so we have to take this radioactive waste, and we have to put it somewhere. We have to store it in special, highly secure locations because it's very, very dangerous to living organisms. That radiation can penetrate your skin, your cells' nuclei, mess up your DNA, cause all types of cancer. So radiation is very, very dangerous. We've got two levels: high level and low level. High level radioactive waste. That's the waste from the fuel rods. So the spent nuclei. The low level radioactive waste. That's all the protective clothing, the tools, the rags, and other items. Both of these things are both of these radioactive wastes are regulated, and what we do with them, that's all controlled by the government. Again, for safety reasons. Radioactive waste has what's called a half-life, and so, for example, uranium-235 has a half-life of 704 million years. So what does that mean? That means that 704 million years from today, this one atom here will only be half as radioactive as it is today. All right, and think about that. 704 million years ago, that's a very, very long time. The dinosaurs went extinct 65 million years ago. So 704 million years ago is a very long time. There are two units that we can use to measure radioactive waste. The becquerel, BQ, that measures the rate at which a sample of radioactive material decays. 1 becquerel equals 1 atom per second. You can also use the Curie, which was named after Marie Curie, who was a very famous scientist and chemist. And that rate is 37 billion decays per second. And we're going to do a whole bunch of math with half-life and radioactive waste in our Do the Math activities that we will work on in class. So don't worry about any of the math right now. Again, we will focus on that in class. Want to briefly talk upon waste storage, radioactive waste storage. And that's primarily in, there was an idea of storing this in Yucca Mountain, Nevada. In 1978, the U.S. Department of Energy began examining a site there. It's 90 miles northwest of Las Vegas, and there was this site was really high on the Department of Energy's list because there was a minimal risk of radiation escape into the environment. It's going to be buried deep underground, be secure from terrorist attacks. But with a recent change in the presidential administration and a lot of protests, the Yucca Mountain project's been canceled. But it raises the question, what do we do with our radioactive waste here? And this is the big idea behind nuclear energy. There hasn't been a new nuclear power plant built in the United States for 30 or 40 years because of all these fears of accidents and the problem of radioactive waste. However, with all the recent problems of climate change, the possibility of looking into nuclear power, that door it potentially may be opening again. Last thing to talk about, something called nuclear fusion. This is different from fission. Fusion is what happens in the stars, in the sun, and that occurs when lighter nuclei are forced together to produce heavier nuclei and heat's released. Okay, so if we take two atoms and we bond them together, we fuse them together, and we release heat, that's fusion. Fusion is very, very promising. Again, that's what happens on the sun, and it's potentially an unlimited source of energy in the future, but we have a lot of difficulty containing the heats that's produced and a lot of difficulty getting that reaction started. It actually takes more energy to start a fusion reaction than we can harness out of it. So right now, we don't have the technical means to undergo fusion reactions, but it is a possibility in the future. Now on the next two slides, this slide here and also on the next one, this goes through an awesome comparison of non-renewable energy fuels. So the chart here has our advantages, disadvantages, pollutant and greenhouse gas emissions, electricity costs and cents per kilowatt hour, and also the energy return on energy investment for oil and gasoline, coal, natural gas, and nuclear energy. You can find this big table on page 337 in your book. Pretty much summarizes what we've discussed in this part, actually in this chapter. And we should be very, very familiar with the pros, the cons, and everything in this table to feel comfortable with the chapter. So once we're done here, again, open up your book, work on your checkpoint questions. How does a nuclear reactor work, and what makes it a desirable energy option? What are the two major concerns about nuclear energy? And what are the promising aspects of and problems with nuclear fission? Go ahead and answer these questions in Edmodo, and this is it for Chapter 12. Once you're done with Chapter 12, you can start to move on to Chapter 13.